Welcome back, and I'm delighted to introduce Barwick to talk about Exodromy.
Thank you. Didn't realize that Cambridge was so close to the sun. All right. Given the fact that it's afternoon and that it's quite hot, you'll probably nod off at least once. So to try and keep things going, I'm talking about stuff that isn't exactly in line with the culture of this room, I expect. So I want to invite you to be combative. Nice.
Right.
But in particular, I mean, all the terms that I have to use have definitions. So I invite you to kind of challenge me on what the definitions are.
Are you starting with the title?
What's that?
Are you going to start with the title?
I will get to the title, but we'll get to that. All right. So let me start with a construction and a theorem. So
What construction? Always more.
I'm already regretting this choice. All right. So here's a construction. So if X is a scheme, then I'm going to build a category. And this is going to be when I say category means category, one category. So gal x, the objects, are going to be geometric points. Spec, I don't know, k going to x, and let me say what I mean by geometric point, because it might not be what you normally think of as geometric points. What I mean by this is that, so K is a separable closure of, well, so if I look at the image of this inside the Zariski topological space here, that has a residue field, and that residue field is kappa, and I'll just call that the image point x0 if this is the point x. Okay, so I'm going to require that this thing be a separable closure of that. So those are the objects. That's all there are.
Could you give me just an example of what I should think of?
Sure, yeah, of course. I mean, so for example, take something like Z brackets X polynomial ring on one generator. And if you take finite,
So you're
in fact, let's not do Z brackets X, so let's just do spec Z for a second. So what am I looking at here? Well, what kinds of points can arise? Well, one thing I can do is I can look at an algebraic closure of a finite field, and that defines a geometric point. Or I can look at an algebraic closure, and that defines a geometric point. And that's the list of all the different geometric points. So that's what the objects are. I have to tell you what the morphisms are. So here. So the morphisms go like this. So let's say that I've got two of these things. So I've got x, let's say goes from spec k to x, and y, which goes from spec L to x. So I've got two of these geometric points. And I want to know what a morphism from x to y is. So a morphism, so I'm going to try and tell you what, I'll say it this way. A map from x to y is, I'm sorry about the scratching, fix that, is a specialization. And the notation I like to use is the squiggly arrow, like that. And I'll tell you what specialization means right now. Oh hell, I've used this board incorrectly already. That way. Okay, so specialization, everybody remember that word because I'm pushing it down. So let me tell you what specialization means. Well, so what specialization means, if I were just talking about points of the Zariski topological space, specialization would mean that X was an element of the closure of Y. Right? The Zariski topological space is not, the points aren't closed, it's not a T1 space or whatever. It points have closures, and those closures can be big. So I'm taking advantage of that now. And so here's what it'll be. So, well, I'll take x, and I've got my point, little x, going into there. By the way, I'll write little x both for the map and for just spec k itself, because I'm being vague like that. And well, what can I do? I can look at the local ring of x at x, and then I can pass to its strict Henselianization. Right, so what does that mean? That means that, well, I've got this local ring, but I've also got an algebraic closure of the residue field. Or, sorry, separable closure of the residue field. And I can take the limit over all the étale covers of that local ring with, with that as a sort of point in every single cover. And this has got a name that's called the strict localization of x. So that has a map going down like this, and well, it's got a map going up like that. And I have y here. Y is just a point of x. It's got nothing to do with little x a priori. But in order for x to be a specialization of y, I require this map right here. And that's the data of the specialization. So this is where the specialization lives.
It's additional structure.
That's the additional structure. That's the data of a map from x to y. It's this map right here that doesn't have to exist, but if it does, then the data of that map is the data of a Okay, so I've given this the name gal x. So let's figure out why I've given it the name gal x. Well, the first thing that I want to point out is that gal x maps down to a poset that you know perfectly well. So this is, by the way, you can compose specializations. If x is a specialization of y and y is a specialization of z, then you can compose that x is a specialization of z in a canonical way. So you can compose these things, and that's the problem. So this is indeed a category attached to my scheme. It's functorial because it looks like it. And so, what can we say about it? So the first thing I can say is the following. Well, if I look at the Zariski topological space with all of its points, this has a natural structure of a poset, a partially ordered set. And what is that structure? That structure is that, well, if I've got two elements, x0, that's supposed to be next, x0, y0 in here, we can say that x0 is less than or equal to y0 if and only if x0 is contained in the closure of y0. This is a specialization structure, too, for points of the Zariski topological space. And here I'm taking specialization structures for some sort of more general geometric points. So with this poset structure, I actually have a functor with a question.
Did you switch the order of x?
I did not. Did I? No, I did not. I think I'm good. X and y are preserved. X here is a specialization of y. So x0 in this case, let's think it through. So x0 in this case, I'm looking at the local ring at x0, and then I've got this guy, and this guy actually lands inside that strict Henselian local ring. That says that x is contained, or the image of x is contained in the image of y. In other words, using this notation down here, x0 is contained in the closure of y0. In other words, I have a functor from gal x down to x zar, where here I'm thinking of x zar with its specialization structure, that poset structure I defined here. So maybe I'll write SP, just to remind you that I mean the specialization poset on the Zariski topological space. And that's a functor. It's more than just a functor, it's actually a conservative functor. Right? Anything that maps down to a single point here is, any map that maps down to a single point here is already an isomorphism back here. What do you think about why that has to be true, but it is. So let's analyze this. What are the fibers of this, first of all? So if I take a point here, x0, right, so that's a point of the Zariski topological space, then what's the fiber look like? Well, the fiber looks like all the possible separable closures of that thing, and all the possible, well, you can see that specializations are quite boring. They're just isomorphisms between the different possible separable closures. So that means the fiber over x0 is the groupoid B of the absolute Galois group of X0. Okay, so that's part of the structure. This thing is somehow a kind of what they call an EI category, or I prefer the term layered category, right? This has the property that it's only endomorphisms are automorphisms, right? So, and I've told you what the fibers look like, and so now I just need to kind of give you the information about the connective tissue. And what does the connective tissue look like? Well, if I've got this relationship downstairs in the specialization coset, if I've got X, which is contained in X0, which is contained in the closure of Y0, then what can I do? I can look at the sections of this thing over that. And that forms a groupoid. And what groupoid is it? It's exactly B of the decomposition group of X0 and Y0. In other words, this gal X is a category that you've constructed from X that consists only of Galois theoretic data. Right? It doesn't have anything, it doesn't know anything else. It knows about the points of your scheme, and it knows about their Galois groups, and it knows about the decomposition groups relatively.
Remind me, what is the decomposition group?
So the decomposition group, well, a priori, it's just a conjugacy class of subgroups of G of Y0. So let's write that. So what happens is that if you have this relationship, then you can look at the absolute Galois group of the residue field of K of Y0. And while I can look at X0, which is contained in this closure, I can look at a point living over it for some finite cover. I can look at a point living over it. And I can look at the stabilizer for that point. And when I look at that stabilizer, that's only defined up to conjugation. But the B of it is perfectly well defined because that was just the base point issue. So I can do that for finite cover. I can also just pass to the universal cover, and the same thing is true. So I have this irreducible thing here. I look at its function field. I look at the absolute Galois group. So I look at the separable closure of that function field. And inside the Galois group, I look at a stabilizer of a point over this guy. And that's giving me the decomposition group, which is another profinite group. And that's the decomposition group that I have here. That's what this is. And that's exactly what you get. Okay, so this is Gal. And it's called Gal because it has something to do with Galois theory. In fact, it has only something to do with Galois theory. It knows about the points, and it knows about these things. So now that I've performed this construction, I guess I have to say one more thing. Well, I just said that these were profinite groups I was talking about. Well, this category that I've written down here also has a topology. That is to say, it's a topology internal to the category of profinite topological space. Okay, so the morphisms and the objects, they have topologies, each of them are profinite topologies. They work just the way you think they do. They're recovering the topologies on these groups here. And, you know, it's a topology. It's a profinite topology. So, let's see what we can do with it. Here's the theorem. We'll let K be a finitely generated field of characteristic 0. And I'm going to look at the following category. I'm going to look at reduced normal schemes of finite type over K.
What's a finitely generated field?
I mean that it's finitely generated as a field. So you imagine taking Q, and you imagine taking some number of field generators, and maybe there's some relations, I don't care how many, that doesn't bother me.
Out of a prime field.
Yeah, finitely generated over the prime field over Q. Other questions about the meaning of that? I'm going to look at reduced schemes. So there's no nilpotence in my structure sheaf. That's important. We look at normal schemes, so I'm not allowing myself nodes or cusps or anything like that. These things need to be regular in codimension 1. And I'm going to look at the assignment that sends X to gal X, this sort of category which only has Galois theoretic data in it. And what is this? This is a category, it's a topological category. And well, of course, I'm working over the space field K, so everything here has an action of G, or equivalently, this lies over Bg of the base field. A topological category that lies over Bg of the base field. And that's the information that I have. And what's the theorem? The theorem is that this is funny thing. That's the main theorem. So what's the meaning of this? Well, one way to understand what the meaning of this is as a kind of Annabelian type statement. So the Annabelian conjectures all have to do with under what circumstances you can take a scheme or a variety and you can recover that variety from purely Galois theoretic information. At the most basic level, it's expected that if you have a curve, let's say a complete curve of genus at least 2, just to be specific, again over one of these finitely generated fields, then you should be able to recover that curve from its absolute Galois group. And there are certain versions of this statement that are actually even known, but you have to be careful about the formulation of them. It's very easy to write something like that wrong, but that's the best. That's the best thing that we have that involves just the Galois group. This is telling you that so these curves are sometimes called Annabelian curves. This is telling you that
Which curves are called Annabelian curves?
well, technically speaking, curves over a field of finitely generated field of characteristic 0 that are hyperbolic, which means that they're Euler characteristic. Well, depending on how you measure it, an Euler characteristic is less than -2. Right, so I can do it with P1, but I have to remove points.
And so then it's a theorem that the Annabelian conjecture holds for these Annabelian curves, or?
Well, almost. So what I mean is that if you look at the set of isomorphisms, maybe I better do this more carefully. If I look at the set of dominant maps from one of these curves to another over K, then those correspond to maps on the pi ones that are invariant with respect to inner automorphisms. So these are the sort of outer maps from one to another. That's the kind of statement that's true. That's a theorem of Mochizuki. But there's this very strict. My point of that is only that there's this very strict geometric condition on that has to show up in order for you to actually get that kind of statement, that kind of ambiguity. This theorem doesn't have any of those conditions. This is for anything that's sort of reasonable. Any smooth variety will do fine. Yeah.
So from X, you can build some kind of category out of the coverings of X. Is this gal related to that at all?
It's related to it, yeah. Yeah, you mean you can look at. Are you thinking of like a tall coverings of this? Yeah. So if you do that, then you'll get strictly less information than this invariant. Right, because for example, coverings, it's possible to have coverings that are branched at certain locations, and I need the information of things that come from branched coverings in this picture. This guy knows all about the branched coverings as well. Other questions about the statement?
So just in what you said to Versa, you can recover that category that she wants from
Sure.
Gal X.
Absolutely. Yeah, absolutely. I guess if you wanted to be sarcastic about it, I could say you could recover anything about your scheme from this category because I can recover the scheme itself, but I'm not going to be. Okay, so this is the theorem, and now this theorem is really just about an ordinary category with a funny topology on it. So it's an understandable theorem. But the way in which we have to prove this theorem, or the way in which I know how to prove this theorem, involves some more machinery. So I need to talk about that machinery. All right.
Could you give us an example? Is there an example to keep in mind?
Sure. Let's do some examples. Well, I mean, here's an example right here. Let's think about this one here. This is the simplest example, but sort of. So let's see what it looks like. So first, let's look at spec Z this Zariski topological space with this specialization poset structure, just so we can understand. This is going to be a very simple poset, and I'm going to draw for you right now. You had a question, right?
There's a field somewhere also. So where's the field now?
So the gal X makes sense for any scheme.
Okay.
I can define it for any scheme.
Okay.
So I thought I'd define it for this one,
Okay.
if that's okay.
Okay. Sure. Okay.
I'm happy to do. Would you prefer I did one over a?
It's just no, in the statement of the theorem, there's a field.
In the statement of the theorem, there's a field, but in the statement of the construction, there's.
That's
okay.
right, yeah.
All right. That's fine.
If maybe, Barwick,
Yes, sir.
I can suggest that you show Noether's theorem as a special case.
Well, okay. I mean,
Up
yeah,
to you,
fair enough.
but
Fair
it
enough.
seems to be this is what kind of people are asking.
I don't know if this is what people are asking. But okay, I mean, let's do it with spec K to start with, or just a field K. So this is going to be extremely boring, right? So this is a very boring poset that looks like that. And then what does gal of spec K look like? It just looks like BGK, and of course it's floating over this in an utterly boring and uninteresting way. Let's do something slightly more interesting. Let's suppose that A is a DVR. So it's a local ring with only one maximal ideal and one other point, which is a generic point. And so let's look at spec of A, ZAR, with the specialization structure. And well, we've only got 2 points. We've got the special point and we've got the generic point, and they're related like that. There's very little happening in this. And well, what does it look like? So I've got this thing line over it, this category line over it, and this category has, well, up to isomorphism, 2 objects. On this object, I have just B of the absolute Galois group of the residue field. And on this one, I have B of the absolute Galois group of the function field. And then I've got the data of a whole bunch of maps going this way. Right? That's what the shape of this category is.
How many can you say? Is it?
Yeah, very much so, because I have the decomposition group, right? And I know that the decomposition group, right, so the picture is the following. I can look at the decomposition group of A. It maps down to the product of these 2 Galois groups. Right, it maps to this one because it's a subgroup of this one, or at least a conjugacy class of subgroups of this one. And it maps to this one because usual Galois theory writes this thing down as the quotient of this modulo the inertial ideal, or the inertial subgroup. This is a quotient of this. This group is a quotient of this. And now, well, if I take these points and look at the fiber over them, then that's exactly my set of maps from this point to this point. There are only two interesting choices here, so I'll just write that.
So when you were being sarcastic, you said you could recover everything from gal of X, but
Yeah.
I can't recover K from the first example, can I? From BGK, I
Indeed,
can't.
you can. That's the point. That's
I
exactly
could
it.
recover the field from the gal. Oh, I see.
Yeah, so that's the, so without the base, that's a harder theorem than this is. This is a medium hard theorem in the 0-dimensional case. And it's, I don't know who to call it, but the version without the base is Neuker-Cuccia. In fact, I really can, just without the base, even recover the field. That's something special about fields. You can't hope for that to happen as soon as you get to something 1 dimension. You need the base as you go up in dimension. If you try and get rid of it, then you end up with something that has to do with birational geometry instead. And I'm trying to recover the full thing. Yeah, so this is the shape of this thing. So this thing is, if you like, it's a quotient set of the product of these 2 modules. That's just what it is.
Right. So this is some sort of nice EI category.
Yeah, exactly. It's an EI category, and it's or as I call them, layered categories. And yeah, I mean, it's really just sort of, horizontally it looks like a poset, and vertically it looks like a group. That's the basic structure that you're looking at here. So the good news is that the story with the DVR, it works fine in for any curve. Like if I have a curve, let's say irreducible. If you like, it can be over your field, but I don't really care. I just need you to understand that it's control dimension 1. This same story is going to hold. I'm going to have the generic point. Well, so what does the post set look like, first of all? Well, the post set, I've got the generic point, and then I have all the special points. Those are the only kind of points I have if I've got the irreducible curve. I've got this big point here, and I've got all the closed points stacked around it, and these are all less than this. Because they're all specializations of it. And well, what happens? Well, here I have the absolute Galois group of the function field, B of it. Here I've got the absolute Galois groups of the residue fields at various places, and then the relationship between them is exactly given by this decomposition. In other words, when I take this category and I map it down to here and I look at sections over this, I get exactly VD for that decomposition curve. And that's the whole of the structure that's going on. So you might think, okay, well, this isn't that exciting a theorem in the curve case because, well, I mean, come on, you gave me all the points. Right? I mean, how much harder can it be to construct a variety if you give me all the points? But one thing that I can point out to you is that if you have two fields of the same cardinality, and you write down two irreducible curves over those fields, then those are homeomorphic as topological spaces. So I haven't given you very much information after all when I gave you the points of the curve. I just told you that it was something one-dimensional.
Maybe this is the same way of asking the same question. What happened to the structure sheaf?
It's not here.
Yeah.
Yeah, I kicked it out. I'm saying that I can recover that just from this information and nothing more. That's the theory. Yeah. That's the concept of this talk. Everybody happy with the assertion?
Yeah.
What's that?
Oh, sorry, no, keep going.
Did you say not yet?
Yeah, but that's the point of the talk.
That is. All right, so how does one prove such a thing? So to do that, I'm going to tell you a slightly.
You can keep the theorem of the black force. Yeah, good.
Oh, sure, yeah. I can just about do that. Actually, that'll give me an excuse not to use this. All right, so the way one proves this, or the way we prove this, is through a long detour through a phenomenon that I'm going to call exodromy. So to tell you about that, I should first remind you what monodromy means. Because the joke is that monodromy is just like exodromy, except I'm going out. So, all right, so what's monodromy? Well, if you have something like, say, a manifold, M, and I look at, say, locally constant sheaves of complex vector spaces on M, then there's this monodromy representation. Let's say it's a connected manifold, and I'm going to choose a base point X. Then I can even write this as representations, complex representations, of pi 1. That's a nice thing to do. Well, if you don't want to choose a point, or if you don't want to demand that you're connected, then you can be Ronnie Brown, and you can say, well, I want to look at representations instead of the group void. It's supposed to be 1. Now, so that's a perfectly fine theorem. This involves all the fundamental groups and all of the connected components all in one place. That's lovely. If I want to do something more sophisticated, if I want to think about local systems not just of complex vector spaces, but say of complexes of vector spaces or something like that, then I need more information here than just pi 1. But I need higher homotopical information. And why is that? Well, that's because, well, even when I just think about what I mean by a sheaf on a manifold, if I'm talking about a sheaf of something like complexes, then I have to be careful with what I mean by gluing, right? Because after all, if I have a section here on the overlap, I only have a homotopy. and on this section, I have a section on this guy, and on these overlaps, 3 overlaps, I only have homotopies. I need to have some coherence law for those 3 homotopies to glue together and make myself a section on everything. And well, as for 3 covers, 3 open sets in my cover, but I don't get to stop. I have to keep doing this. And so that tells you that, well, first of all, that you have to be careful about what you mean by sheaf. But it also tells you that when you're moving, so how does this monodromy equivalence work? Well, I take a loop and I take a section of the vector bundle over that point, and I transport it parallelly around this, and I get back to something that either looks the same or doesn't, and that gives me my action. And that action, if I'm now working in a homotopical setting, that action actually depends on what precise homotopy I used. If, let's say that this is contractible, but let's say it's contractible in 2 different ways because I'm on a 2-sphere, then that choice is actually going to be a non-trivial choice and can give you 2 different, you know what I'm saying. What I'm saying is that if I now look at local systems, not just of complex vector spaces, but if say complexes in something, I don't care, then this is really representations of the fundamental infinity group void. So maybe just to say it this way, it really functors from pi infinity m into, well, whatever I put there, complexes. And as you can see by my increasing cavalierness about this, anything can go here as long as it's the infinity category. This is a perfectly sensible statement, and it happens to be true. So yeah, I mean, this means locally constant sheaves with complexes. And this means functors from here. So this is an infinity category. Not a priori, right? I mean, I agree with you that you know, guys like you probably would prefer to just have these 2 be equal.
When you make a vector bundle out of patching things together, saying something then.
Yeah. No, I mean, it does mean something to talk about a sheaf of spaces, and then okay. So here's a non-trivial statement, right? So I can look at the category of sheaves of spaces on M, and I'm telling you that functors from here into spaces embeds fully faithfully, and I'm identifying the essential image of that functor. So there's a sentence in there that's slightly non-trivial. Okay, so this is the monodromy equivalence, right? And monodromy refers to the fact that, well, you're saying based at one single point and you're walking around, right? So the dromos is supposed to refer to the fact that you're taking a path from one place to another. So what's the story with exodromy? In the exodromy story, I don't just have a topological space, I have a nice stratified space. So, so by stratified space, I mean, we give a definition, a p-stratified topological space is a continuous map from X to P, where here I'm giving P the Alexandrov topology. P is a poset. Any poset you like. And the Alexandrov topology is the one in which the open sets are the ones that are they're cosieves. They're the things where if you have 2 elements X and Y, and X is less than or equal to Y, and X is in your open set, then Y has to be in your open set as well. That's the topology I'm going to put on here. So, simple example, think about, well, the poset that we had on the board before, this boring poset here. The Alexandrov topology is giving you the Sierpinski space, with this point is closed and this point is open. And what is a P stratification if this is P? Well, it's just giving you the closed and the open complement, and nothing more. Situation. So that's what a P stratified topological space is. And now if I want to talk about sheaves on a p-stratified topological space, I don't want to talk about locally constant sheaves. Because local constancy is something that I only want to ensure stratum-wise. So it's a bigger class of sheaves, and they're called constructible sheaves. So a sheaf, F, and I don't really care what the target category is. If you like sheaf of spaces, it's fine. On X is P constructible. When I take F and I restrict it to the inverse image of a point here, that's called a stratum, then, so I'll call that X little p, then this is locally constant. Well, and I'm being a little crappy here because really constructibility usually involves a finiteness condition as well, so let me say something like formally p constructible. The finiteness condition will appear in a minute. Okay, so those are the definitions. What's the theorem? So the theorem, and in the one category case, this is the theorem of an unpublished theorem, I think, of Bob McPherson. In the two category cases, is due to David Truman, and in the infinity category case, is due to Jacob Lurie. So. And with the statement is that, well, if I look at the category of constructible sheaves on X, and this time let me go ahead and specify that I'm valuing spaces as I will be from now on, then these are also a functor category. You can ask what functor category is it? This functor's out of a category that I want to call pi infinity 1p of X, and I'll tell you what this is in one moment in the spaces. So what's pi infinity 1p? Well, before I had the fundamental groupoid, and in the fundamental groupoid I had the objects of my topological space. The objects were points of my topological space. The morphisms were paths. The two morphisms were homotopies of paths. The three morphisms were homotopies of homotopies, et cetera, et cetera. Now, in this context, I'm going to do the same thing, except I need to keep the stratification in mind. So these are going to be, rather than just paths, they're going to be exit paths. That is to say, I'm going to look at paths. So here's a morphism of this. So the objects are going to be the same. The objects are, again, points of my X. But the morphisms, let's say this is a point little x and a point little y, the morphisms are going to be paths from here to here that go out, right? So if this is an enclosed stratum, this needs to be in an open stratum, or in a more open stratum. Right? They need to be compatible with the direction on the post set that you have downstairs. These are the exit paths. And the homotopies need to be exit path homotopies, and the homotopies of homotopies need to be exit
Just to
path
get the
homotopies.
dictionary right, that's going downwards.
Yeah, sorry. Yeah, the 0 is closed and 1 is open, so I'm going out when I go this direction. Yeah, sorry. I don't know why I write my post-its vertically. It's not good.
Because up is bigger than something higher is bigger than something up.
Yeah. And restructure myself.
Can you stay in the same stratum?
You can stay in the same stratum, that's perfectly allowed. You're permitted to stay there if you want. You don't have to leave. You can stay right where you are. But if you do leave, you can't come back. So it's like a high school lock-in or something like that. If you leave, you're not coming back. And that's the nature of these exit paths. And the exodromy story is really saying that exit paths are running the show as far as constructive sheaves are concerned. That's why I use the term exodromy. Exo meaning to go out, and dromy meaning to run, or maybe it means avenue in ancient Greek. And you're running out with these paths. And the story is exactly the same, right? If I have a constructible sheaf, let's say I'm thinking of a constructible sheaf of just vector spaces to start with, so then I don't need the whole fancy structure here. I can actually just work with the one category. There's nothing wrong with that. And what will I do? I'm going to take a vector and I'm going to parallelly transport it out. I'm going to see what happens. I might not be able to come back though, because it might not be a locally constant sheaf of vector spaces. Right? It might only be locally constant stratum to stratum. So this is lying in substratum, some closed stratum, and this is outside that. And I might not be able to have a way to get back in a parallel fashion. Okay, so this is the exotropy story.
Sorry. For the homotopies between the paths,
Yes.
what does it mean for them to exit somehow?
Yeah, so let's see if I can write down the precise thing here. So let me just think for a second. Yeah, okay. So I mean, I'm going to work with models here for a second. So my pi infinity is, I'm really going to take the singular complex of x. It's just the thing that I described, and that maps down to sing of p, which is a weird thing to do. So you're taking this post set, you're regarding it as a topological space, and then you're taking the sing of it, right? So in this case, you're getting an interval, right? But now I want to have information that says that 0 is a special point relative to the rest of that interval, right? I'm trying to retain that information. So what do I do? Well, it turns out that I have a nice map coming from the nerve of p into this simplicial set. Right? And you can see exactly what it is in this case, right? It's telling you that this is the special point, and then I've got this. And so then, so I've got this special thing happening here, and then this is the literal fiber product of this diagram. So seeing p of x, this is the literal fiber product of this diagram. So when I talk about a path, I have to give you a path downstairs and a homotopy, or a path in the space from one point to another. And if I want to give you a homotopy of paths, well, then I'm trying to give you a delta 2, or kind of a crushed delta 2 down here. So I have to give you the crushed delta 2 in NP, right? And then I have to give you a homotopy that that respects the structure map down to NP the whole time. So that's what I mean. So this is actually just the literal set theoretic definition of this thing. Not working up the homotopy or anything. Okay, so this is exodromy in the topological case. So this is how you get constructible sheaves on stratified topological spaces. Now what I want to do is I want to port this whole story over to the world of algebraic geometry in order to understand schemes in the same way. So let me say a couple things about that. I'm moving pretty slowly, but I'm going to keep doing that. Yeah, so how do I port this story? Well, so first, let me remind you how you port the monodromy story. So in the monodromy story, you are unable to work with the Zariski topology in order to, understand things like the fundamental group of the scheme. That's because the Zariski topology isn't a particularly good topology from the homotopy point of view. So instead, what you do is you monodromy equivalence. So remember, you have this monodromy equivalence that says that you're looking at local systems and you're writing those down as representations of pi 1. So what you do is you look at local systems on your scheme, but those local systems are Atoll local systems. They're local systems for the Atoll topology. And that is the definition of pi 1. Right? If you wanted to, you could be, if you were a very aggressive lecturer in your algebraic topology class, you could come in and you could say, well, okay, here's the definition of pi 1. I'm going to write down a functor from categories to categories. And it's going to send any category to the category of local systems on your manifold. And that functor is representable, and the representing object is the fundamental groupoid. Class dismissed. And I think this would not be a good idea, but you could, in theory, do it. And in algebraic geometry, you don't have a choice. That is the way you have to do it. Is that understandable? You're either tired or both. Both always useful. Is it clear? So I'm trying to port this story over into this context in the same way. all I'm trying to do. Okay, so now, so I have my scheme. Now let's X be a scheme. And I'm going to look at the atoll topos on it. So this is a category. The objects are sheaves for the atoll topology. You can look at the locally constant ones. The locally constant ones are the ones that correspond to representations of the fundamental group. But I want to do something more sophisticated. I want to extract constructible sheaves. Now, there's a point here, the divergence between the way topologists use the word constructible and the way algebraic geometers use the word constructible. But it's not as serious as you might think. So what an algebraic geometer means when he or she says a constructible sheaf is a sheaf along such that there exists a finite constructible stratification of the scheme such that when you restrict your sheaf to the strata, you get something locally constant. So that there is no chosen stratification that you're working with. So that's not as bad as it might seem because of the following observation, which is that this is a old theorem of Hoxter, which is that if X is quasi-compact and quasi-separated, then, the Zariski topological space is actually the limit of its finite constructible stratifications. In fact, that's a full characterization of what the Zariski topological spaces look like. The Zariski topological spaces are exactly the same things as profinite posets. There's no difference between these two things. They're profinite posets and nothing more. So
we written just above X to P.
that's Exodromy, the topological space associated with X.
Exodromy.
Yeah. And this is supposed to say finite constructible stratification. Okay, so that's exactly the story, right? Is that we're now going to look at this system of all the finite constructible stratifications. We're going to look at constructible sheaves relative to those stratifications, and we're going to take the colimit of that diagram. And the resulting colimit is going to be what people or algebraic geometers normally call constructible sheaves. So if you like, you can think about stratification not just with respect to posets, but with respect to profinite posets, and that's exactly what we end up doing. Okay, so we've addressed one issue with porting this over. The next issue is how do we define this thing? And we're going to define it in exactly the same way. So the Exodromy theorem is that there exists. Well, let me do it first for a finite poset. So if X is a quasi-compact, quasi-separated scheme, and X to P is a finite constructible stratification, then, well, what happens? I can look at constructible sheaves for the atoll topology that are constructible relative to this P. And what are they? Well, they're the same things as functors in the spaces, but now I'm going to have to modify this a little bit. I'm going to have to be careful because one of the problems that you immediately encounter when you try and port things to the algebraic geometric world is that you can't just expect to get, say, a fundamental group in the ordinary sense. You have to get something a little more sophisticated. You have to get either a pro group or a profinite group. For the purposes of this talk, I'll just focus on the profinite part of the story. So, and then you only can get representations into things with torsion coefficients and get a monodromy theorem there. So that same thing's going to happen here. I'm going to have to work with pi finite spaces instead of arbitrary topological or arbitrary spaces. But then I can write here. I'm going to put a little hat here to remind me that it's profinite. and I'll put a P up here and an atoll there. So what's going on here? So I'm looking at the category of pi finite spaces, and here I'm looking at a pro-finite infinity 1 category. And this is pi infinity 1 P at of x.
P is still just a poset, you're not
P right now
specifying
is just a
stratification.
Yeah, no, it's just a finite constructible stratification right now.
So when you put on that side, these are ATOL for that particular stratification, not just for P. You've specified the map from X to P.
I specified the map from X to P, and I'm saying that I'm looking at an atoll sheaf with the property that it's locally constant on the strata. That's all I've done. And this thing is actually a functor category. Well, if I take pro objects, I can actually regard it as a functor category. This is the exodromy here. This is not just true for finite constructible stratifications, it's also true for pro-finite stratifications, which means that you can relax even more. And if you want to just talk about all constructible sheaves, well, this is just a colimit over all these P's, so you land here. And again, this is just a pro-finite infinity 1 category attached to your favorite scheme. And this is the exodromy theorem. So, what does this thing look like? We have to find out some way to analyze this thing. In particular, we have to be able to say something non-trivial about it in some examples. So what does it look like? Well, this is actually a 1 category, as it turns out.
Sorry, can I?
Yeah, please.
What did pi finite mean?
Oh, pi finite means that if you only have finitely many connected components, and for each of those, you only have finitely many homotopy groups, each of which is finite. Here. Why is it?
Yeah, why is it still pi finite instead of all?
I can produce a version that works for all of them, but I still have a pro thing here. And anyway, I mean, since you can recover schemes from the pro finite version rather than the pro, like I can have a pro category here instead of a pro finite category here. Right? I can do that, but it turns out that doesn't really give you any extra information in the situation that I'm describing. So I'm not stressed about that. And the reason for this is that there's I don't know how much you want to hear about this, but there's a reason for this, which is that there's an infinity categorical form of Hochster duality. Hochster duality tells you that profinite posets are the same things as spectral topological spaces. And I'm going to give you a characterization of spectral infinity topoi. And those things are picked up by profinite infinity 1 categories. And that's what's playing in the background here. I'm not saying that. That's what's back here. But I wanted to focus on actually computing this thing. And I'm going to tell you the surprise that it's in fact just it's not as sophisticated as it might look. It's just an ordinary 1 category. And it's the 1 category that I started with. It's a profinite 1 category, so that's why I had to put this topology on there. But once you do, that's all there is to it. So here's the kind of the theorem that runs things. Here's the main theorem. But here's the sort of, if you like, this is the main technical theorem. This is an infinity process. So, if you look at the category of profinite spaces, and I'm just going to stop writing the whole word space. This is the pro category in finite spaces, an infinity category. And this actually embeds fully faithfully into the category of infinity topoi.
Sorry, you just explained what S pi hat meant. Could you say it again?
Yeah, it's the category of profinite spaces. Right, so this is pro objects in pi finite spaces. And this infinity category actually embeds fully faithfully into the category of infinity topoi. And how does it do that? Well, if I have a pi finite space, I can just look at functors from that pi finite space into spaces. That's an infinity topos. That's it. And then for the pro things, I just extend as I'm supposed to. This is actually fully faithful in fact. Moreover, you can characterize the kinds of infinity topoi you get. You can say very precisely what kinds of, there's a recognition principle for these infinity topoi. It's a list of kind of irritating technical conditions, but basically, these things have to have very strong finiteness conditions. They have to be what's called bounded and coherent. And they have to have the special property that the small objects inside there, the coherent objects inside there, have to be the local systems. They have to be locally constant sheaves on that topos. So the idea is very, very simple. You're just going to take, instead of profinite spaces, you're going to take profinite stratified spaces. And you're going to put them into a category of stratified infinity topoi. And that's actually going to be fully faithful once again. And moreover, you can characterize the essential image. The essential image consists of, again, there are these finiteness conditions bounded to coherence. And then one other condition, and that other condition is guaranteeing the small objects, the coherent objects, are exactly the constructible sheaves. Operates exactly as this, except with stratifications everywhere. It's really just a perfectly clean analogy.
So
Yeah.
just to verify, right? So if you remove the head there, stratified by finite category, this means there's a finite poset.
Yep.
You map into it, and all mapping spaces are by finite.
That's right. Exactly correct. And I need finitely many objects upstairs too.
Yeah.
Up down surface. Yeah. Exactly. So each stratum is pi finite, if you like.
Could you repeat the condition on small objects? So
Yes, the condition here, so the essential image, let me just write it down, are, these are stratified infinity topoi. That are bounded coherent. This is just a finiteness hypothesis. And the finite objects, so if the stratified topos is called X, then if I look at the objects that are coherent and truncated, these are exactly the constructible sheaves. This is always the constructible sheaves automatically have these finiteness hypotheses, but it's not obvious that this should be inequality. In general, it isn't. But if you're in the essential image of this, then you are. Now, okay, why is this an interesting theorem?
So,
Yeah.
and on the left, do you have the assumption that the factor to the poset is conservative as well?
Yeah, that's part of what it means to be a stratified space. So I'm funneling stratified spaces through this pi infinity one, and that always has a conservative functor down to the cosine. So I'm almost out of time, but let me tell you what the relevance of this is, why you can actually extract a theorem like this. The point is that there's an example that we all know and love of these things, which is that if S is a scheme, and again, quasi-compact and quasi-separated, this is just a topological constraint, then its tall topos, as regarded as an infinity topos, is in this essential image. Okay, so what does that tell you? That tells you that that everything about the scheme that can be gotten from its Attal topos can be gotten from the associated stratified space, or profinite stratified space, which is this guy. So everything about the Attal topos can be reconstructed from that. And then you merge that with a theorem of Voevodsky that says that for reduced normal schemes, everything about the scheme can be reconstructed from the Attal topos. And that's how you prove the theorem. Seems like a good place to stop.
are there all kinds? Questions?
This is nearly combative.
This last step seems less than obvious.
Yeah.
Do you have a two-sentence explanation
Which last step?
for why that's true?
Why these things are the essential image? Yeah, that's very much less than obvious. So the argument is, this is one characterization of this essential image. Another better characterization of this essential image is that these are the stratified topoi with the property that the strata, and now these are over profile, the strata are actually stone infinity topoi. They're in the essential image of this functor. And so if I take a scheme and I map down to the, I take the tall topos and map it down to the Zariski topos, and I look at a fiber, then that's just a BG as a topos. And so that's the argument. But no, you're right. Seeing, I mean, the difficulty is sort of embedded in the different characterizations of this essential image. We sort of move these blocks around here, and then once we move them around in the right way, it became obvious. This would be an example. But that's why you want to have a number of different characterizations of this essential image. Yeah.
So if I want, let's say, to represent the line numbers, I want some object corresponding to BGM, one of the categories that you faithfully embed. Do you know if that works?
I think I know that doesn't. If you want the whole BGM, I think I know that doesn't work.
You can only see the roots of unity.
You can only see the sort of hidden finite part of BGM.
Some of the information is there, okay, but the fact that it's only faithfully embedded. You're saying there's no.
Wait, so let me make sure that I understand the question. So you're saying take BGM as a stack, right?
I'm saying, yeah, take BGM as a stack and try to push it into, well, you had one to finite topological categories over BGK, and the other one into stratified infinity topoi. Well, my guess is the first one, there's no chance you can push BGM. That's just not gonna happen.
It's not gonna happen, that's right.
But maybe in the second one,
I wouldn't like to say. I don't know. I don't know. I don't have the answer. Maybe use on
So you said your theorem had a name in the case, like a special case of a point, which you did as an example. Can you see where that, like, you gave the example of, just the field, right? So,
Yeah, so in the case of, well,
so that there was this question why you could recover the field from this Galois group. So
right, but you're not just, I mean, in this theorem, you're not just recovering it from just the Galois group. You're
Right,
recovering it
just
from the
Galois
Galois
data.
group along with the information of GQ acting on it.
right.
Right. So I mean, if take two number fields K and L, I'm saying that if you know that GK is isomorphic to GL as GQ groups, then you can.
What's GQ?
Let me write down. I'm going to write things down instead of waiting. I'm saying that if these things are isomorphic as groups with an axiom of GQ, then K is isomorphic to L.
no, I can write a map, an embedding.
Well, I mean here, there's no difference, right? Or, if you like BGK and BGL, if these two things are the same with this action of GQ, then this happens. Now, the Noether-Uchida theorem actually allows me to cover this up, which isn't something that my theorem allows me to do. So, the hard part of their theorem is that you can cover this up.
Okay, so you can't recover that theorem.
Yeah, I can't quite recover that theorem. And I wouldn't expect these techniques alone to do that. This is really more about high-dimensional schemes. Right? And in high-dimensional schemes, you can't hope to recover the scheme without the information about the base field, the Galois group of base field acting. There's just no hope. Even for curves, you already run into trouble. They're birational statements.
Hmm.
So Florian Pop has a birational statement that says that you can recover. Oh gosh, don't make me say this statement because I can't remember the specifics. There's a complicated statement that says that effectively that you can recover a curve up to birational equivalence from its absolute Galois group. But only certain kinds of curves and only certain kinds of information are permitted. So let me not try and state precisely because I can't remember.
In the theorem, you require characteristic 0.
Yes.
When you continued, it was very obvious to have 0.
It wasn't used anywhere until the very final step. The very final step involves the difference between a scheme and its Untitled topos. And there's this sort of tension there. So let me give you an example in characteristic P where you start to run into problems. So if I take let's say that I'm working on a field of characteristic P and I take the Frobenius and I pull back my scheme along the Frobenius. I get a new scheme. It's not the same as the original scheme, but their Untitled topoi are equivalent. That means there's no hope to recover it from any of these kinds of invariants. So what you do, if you want to write down a statement like this, is you try to pass to the perfection. So you take something like, so if you think of the affine line over FP, right? So that's FP brackets T. I'm going to add on all the P fruits to that thing. So I need to have all my residue fields have to be perfect, including the ones that the generic ones. So I'm going to do this perfection process. And I'm going to get myself some gigantic scheme. It's not going to be Noetherian anymore, but it'll exist just fine. And the conjecture, and it's still just a conjecture, is that that's still recoverable in the same way. It's the statement, I mean, there's an integral statement as well, that's in the paper, which is a conjecture. I really love it, it doesn't help me solve it. It's got to be true, but I just have to.
So I think it's coming to a time when further discussion should be adjourned to the hub, but we should thank Clark again